Today's video I am going to explain intermediate value theorem. Here is the statement. If f is continuous on closed AB and f of a not equal to f of b, then f takes every value between f of a and f of b. Here then plays a vital role in the theorems. So before then it was given and after then we have to prove. See here, f is continuous on closed AB is given and f of a not equal to f of b. Then we have to take f takes every value between f of a and f of b. See here, it is the another statement. If f is continuous on closed AB and k be any real number between f of a and f of b, then see here, so then we have to consider that before then it is given. What is given? F is continuous on closed AB is given and k be a real number between f of a and f of b. What we have to show? Then there exists C belongs to open A comma B such that f of C is equal to k. See here, first of all, what is given I am writing. So f is continuous on closed AB. From the statement I am writing that f is continuous. F is continuous on closed AB and k be any real number. So k be any real number between f of a and f of b. So what is it given? So k lies between f of a and f of b and f is continuous on closed AB is given. Now I am going to consider a set. So which set I am going to consider? See here, let S is equal to, the set here I am assuming as x belongs to closed A comma B such that f of x minus k less than 0. So this is the set. Whenever we choose a set, so we have to show that it is non-empty. So I am taking A. So A belongs to, since A belongs to closed A comma B, and from this statement f of A less than k, which implies f of A less than k. From this we can conclude that f of A minus k less than 0. Got it? So in this case, so if f of x minus k is less than 0, so those elements will exist in S. So here f of a minus k is less than 0. Therefore a belongs to S. So I have created a set here and I have shown that one element is there. From this we state that S is non-empty. See here, it's a non-empty set. So the first thing is S is non-empty. Next, since B also belongs to closed A comma B, implies, so from this statement, see here, from this statement k less than f of b. So f of b minus k is greater than 0. So it doesn't exist in this set because f of x minus k less than 0, only those elements only will exist in this set, whereas f of b minus k greater than 0 does not exist. So b belongs to closed A comma b such that f of b is greater than k. Therefore b is the upper bound of, so b is an upper bound of S. So this is statement number 2. So from 1 and 2, see here, from 1 as well as 2, so S is non-empty, the set is non-empty, it is a non-empty set and has an upper bound according to which statement? So by completeness axiom. So which axiom? By completeness. So by completeness axiom, S has supremum. So S has supremum. So what is that supremum? So we have to suppose let supremum of S is equal to C. So which implies that f of c minus k less than 0 and f of c is less than k. So this is most important thing. See here, according to the textbook, so these are the steps taken. See, first of all, f is continuous is given on closed AB and k is a real number between f of a and f of b. So it means that k lies between f of a and f of b. So now we have to suppose a set is there, x belongs to closed a comma b such that f of x minus k is less than 0. Since a belongs to closed a comma b, and from this statement f of a less than k, f of a less than k, so a belongs to set S. So we have taken one set and we have shown one element a is there in it. Therefore S is non-empty set. Since b belongs to closed a comma b, see from this statement k less than f of b, so we have f of b minus k is greater than 0. So b belongs to closed a comma b such that f of b is greater than k. Therefore b is an upper bound of S from 1 and 2. If S is non-empty and has an upper bound, by completeness axiom, S has a supremum. So we have to suppose that the supremum is C. So for this set, if C is a supremum, then f of c minus k is less than 0 and f of c is less than k. And the thing here is, after then we have to show that, after then what we have to show that c belongs to open a comma b. So c lies between a comma b, that is a less than c less than b. So we have to show that c lies between a comma b, and after that we have to show that f of c is equal to k. For that the next step will be, see here, now c is the supremum and f of c is equal to, so f of c is equal to, so f of c is less than k. So remember this one. And the next one, since what is given, f is continuous on closed AB. So f is continuous on closed AB. Then f is continuous at right of a. See here, at right of a. See here, this is a and this is b. Closed AB. So this is a minus delta and this is a plus delta. So this will be a plus delta. Since f is continuous from a to b, so f is continuous from right side of a. So right side of a means f is continuous at, see here, f is continuous at x belongs to a comma a plus delta, right side of a. So according to this we have to choose an epsilon. So epsilon is equal to, I am choosing that k minus f of a. So if it's continuous, according to the definition, for given epsilon is equal to k minus f of a, epsilon greater than 0, there exists delta greater than 0 such that, see here, such that according to the definition of the continuity, x belongs to S, comma x belongs to a comma a plus delta. So this is very easy to understand. If you follow this video, it will immensely help you. That is f of x minus f of a less than epsilon. So which means that, so f of a lies between f of x minus epsilon and f of x plus epsilon. See, look here. So it's so simple. The next statement is f is continuous on closed AB. If it's continuous, it should be continuous on each and every point. So f is continuous on right side of A. So this is the right side. So I'm neglecting this one. So from A to B, right side of A, according to the definition, have chosen epsilon is equal to k minus alpha. So now see what happens here. So f of x lies between, see here, f of a minus epsilon and f of a plus epsilon. See, the statement here is f of a minus epsilon and f of a plus epsilon. Now I'm choosing this one. So f of x less than f of a plus epsilon. So now f of x less than f of a. What is epsilon value here? Epsilon value is nothing but k minus f of a. So this is k minus f of a. Now I'll cancel this plus and minus, and f of x is less than k. See here, f of x is less than k, which means that f of x minus k is less than 0. See here, if you observe, f is continuous on closed A comma B. I am taking f is continuous at right side of A. This is A plus delta. So here C is the supreme. Therefore A belongs to this. F of A minus K is less than 0. See here C is the supremum. In this case I have taken a set here. So in this case f of A minus K, A belongs to this set and C is the supremum. So what is the relation? So A is less than the supremum. So the relation here is A less than C. Next what we have to show that so we have to prove that A less than C less than B. So now we have to show that to prove that C less than B. So for that let us suppose that if possible suppose that C is equal to B. So I am taking C is equal to B. See here, according to our statement, proof by contradiction, C is equal to B. And see what happens here. So again you know that f is continuous on closed AB. F is continuous on closed AB. Then we say that, see here it is A and this is B. See here, this is B minus delta and outside it will be B plus delta. So I am telling that f is continuous. See here, f is continuous from left of B. So from left side of B. So this is the left part, f is continuous in each and every part. Here there is delta plus he. So this is left side and see here from A it is right side. So according to the definition, so x belongs to, since x belongs to B minus delta comma B, which is a subset to closed A comma B, which implies that f of x minus k is greater than 0. So I have taken this statement. So k is less than, see here, k is less than f of b. So f of b minus k is greater than 0. So after b, so c lies in between f of a and f of b given. Since it is given that f of a less than k less than f of b. So it is given in the statement that f of a less than k less than f of b. So from this, if it's between k, see here what is the relation? So f of b, see here f of b minus k is greater than 0. So now I have taken b is equal to c. See here c is equal to b. So b is equal to c I have taken. So I am writing in place of b as c. So x belongs to, this is c minus delta c, which is subset to closed a comma b, such that again, so f of c minus k is greater than 0. Since c is the supremum of the set, so we have f of c less than k. So we have a statement, very important statement, since c is the supremum of the set, f of c is less than k. But we got here as, see here, we got here as f of c is greater than k, which is a contradiction. So why we got a contradiction? Which is a contradiction since f of c is always less than k. See here, it is less than, f of c is less than k. Why we got a contradiction? Because our supposition c is equal to b is false. Therefore, our supposition, see here, our supposition b is equal to c is false. Therefore, see here, c is less than b. So according to the statement we have, if it's a contradiction, then b is not equal to c. Therefore, c is less than b. So this is, see here, this statement we can name it as a 3 and this is 4. So 1 and 2 are completed. From 3 and 4, we say that a less than c less than b. So this is, according to the problems, half of the Problem is completed. So C lies between A and B. Now next we have to show that. See here, next we have to show that. Next we have to prove that f of C is equal to K. So we have to prove that f of C is equal to K. Next, if possible, suppose that, again proof by contradiction. If possible, suppose that f of C is less than K. Then what happens? F of C minus K is less than 0. Since f is continuous, again since f is continuous on closed A comma B, then f is continuous. See here, f is continuous at a point C. Then there exists delta positive such that, see here, according to the definition, x belongs to C minus delta comma C plus delta implies f of x minus k is less than 0. According to the definition of the continuity, f of x minus k less than 0. See here, when you observe the same thing, this is C, and so this will be C minus delta and this is C plus delta. So in between this statement, so in between this set, so f is continuous everywhere, so that f of x minus k is less than 0. Now I am choosing certain point alpha. So here from this whole statement, f of x is less than k. See here, then let alpha belongs to C minus delta C plus delta such that according to this statement, f of alpha minus k is less than 0. Then alpha, see here, C is the supremum value in the set S. According to the supremum, we have f of C minus k is equal to 0. But there is another point alpha which is making the same statement. Then alpha is the supremum. Then alpha is the supremum, which is a contradiction. So which is a contradiction? Which is a contradiction to the statement that, which is a contradiction to supremum of S is equal to C. So why we got a contradiction? Because our supposition f of C is less than K is false. Therefore our supposition f of C is less than K is false. Therefore f of C is equal to K. So f of C is equal to K is shown in this. Therefore the next one, we have to choose the second case. See here, this is all from the first case. From the first case we have proved that A less than C less than B and f of C is equal to K. So this is case number 1. So this is case 1. According to the case 1, we have f of C is less than f of A. So this is case 1. According to this case, f of A less than K less than. Now according to the case 2, see here. So according to this case, so we have f of A. So f of A less than, this is f of B. And now in the second case, so what is this case here? So according to the second case, we have f of A is greater than f of B, and we have a real number k such that which lies between f of A and f of B. Therefore f of A is greater than k, greater than f of B. See here, now I am multiplying the whole inequality with minus. This is minus f of A less than minus k less than minus f of B. And the next one, what we have to define? Now I am going to define, see here, now define a function f maps, capital F maps from closed AB to R such that capital F of x is equal to small f of x. for every x belongs to closed A comma B. Now see here, f is continuous on closed AB. See here, it is given in the statement that f is continuous on closed A comma B. Now even if I multiply with a constant -1, it is continuous on closed A comma B. It is continuous on closed A comma B. Minus f is nothing but capital F of x. Therefore capital F is continuous. See here, it is continuous on closed A comma B. According to the case 1, just now I have proved, according to this case 1, if f is continuous on closed AB, there exists a point C lies between A and B such that f of C is equal to K. Here f of C is equal to C here. So what is there here? The K value is negative sign. So this is minus K. So capital F of C is equal to minus K, and in place of capital F of X, so we can write as capital F of X is nothing but minus F of X. So this will be minus F of X. So this is minus F of C, this is minus K. If I cancel minus on both sides, we get F of C is equal to K. So this is how we have to solve, and this is the whole theorem from the textbook. So thank you so much for watching, and just let me explain you once again. See here, what is given in the statement? F is continuous on closed AB is given, and K is any real number between f of A and f of B. Then there exists C belongs to open AB such that f of C is equal to K. Remember, so before then it is given. So what is given? F is continuous on closed AB is given, and K is a real number between f of A and f of B. So first of all, I am writing what is given. So f is continuous on closed AB, and K is any real number between f of A and f of B. So first case I am taking as f of A. So if you observe this one, there are three cases between f of A and f of B. Either they are equal or less than or greater than. So these are the, according to the law of trichotomy, relation between any two values is either less than or equal or greater than. So it is given that f of A is not equal to f of B from the statement here. F of A is not equal to f of B. So this is given. So there will be case 1 and case 2. So according to the case 1, we have to take f of A and f of B and prove, and next one f of A greater than f of B. So the case 1 here is f of A is less than f of B. A set S is defined here like this, f of A minus K less than 0. So if A belongs to closed A comma B, f of A less than K. So from this we have f of A is less than K and f of A minus K less than B. If this condition satisfies, A belongs to set S. So S is non-empty set. And according to this one, K less than f of B. So K doesn't belongs to S, and K acts as an upper bound of the set S. From 1 and 2, if S is non-empty set and it has an upper bound, by completeness axiom, S has a supremum. So according to the supremum, we have C is the maximum value, and we don't have any other value which is greater than C. So this is the statement which you have to keep in mind. And next one, f is continuous on closed AB. So f is continuous from right side of AB. So this is right side, A plus delta. So f belongs to A comma A plus delta. So I have chosen epsilon is equal to K minus f of A. For given epsilon greater than 0, there exists delta positive such that x belongs to S. X belongs to A comma A plus delta, implies f of x minus f of A less than epsilon. So which means that f of x value lies between f of A minus epsilon and f of A plus epsilon. Here what is the value of epsilon? K minus f of A. So if I substitute and cancel, f of x less than K. So which implies that f of x minus K less than 0. So f of A belongs to the set S. Since A belongs to set S and C is supremum, it is the supremum value, then what is the relation between these? A less than C. Next we have to prove that C lies between A and B. So this is made, and we have to show that C is less than B. So we have to prove that C is less than B. For that I am supposing that C is equal to B. So again f is continuous on closed AB. So here from B, it is continuous from left side of B. from left B. So x belongs to B minus A, B. So which is a subset to AB, and here from B side f of A minus k is greater than 0. So f of B minus k is greater than 0 according to our condition here. So according to our condition, we have taken that f of A less than k less than f of B. So here this will be f of B minus k is positive. Since B is equal to C, we have f of C minus k positive. Then f of C is greater than k. So we have shown that f of C is less than k here. And now what happens here? F of C is greater than k. So this happened because our supposition B is equal to C is false. So we have to accept that B is less than C. So B is not equal to C and C is less than B from 3 and 4. So this is the statement 3 and this is the statement. So we accepted that C lies between A and B. Next we have to show that f of C is equal to K. So if possible, suppose that f of C is less than K. Again, proof by contradiction. So if I make a contradiction and just again I'll accept the reality that f of C is equal to K. So again we have a single statement that f is continuous on closed AB. So f is continuous at a point C. So between the neighborhood values, that is C minus delta and C plus delta, f is continuous. So I am taking the value alpha from C to C plus delta. So which again states that f of alpha minus k is less than 0. Since C is the supremum of the set, yes, alpha is also supremum. So we got another supremum here because our supposition that f of C is less than k is false. So we have to accept that f of C is equal to k. So we got a statement that C lies between A comma B and f of C is equal to k according to the intermediate value theorem. And here is the case 2. So the next case 2 is, so for less than it is accepted, for greater than we have to take. So according to the case 2, f of A greater than f of B. So here f of A greater than, so k lies between f of A and f of B. So I multiplied with minus k here. So in place of minus, so we have to write as capital F of A. So here, so this statement will be capital F of A less than, here this is minus k less than, and again this is capital F of B. Since f is continuous, minus 1 into f, if I multiply with a constant, then also it is continuous. Therefore, capital F of x is continuous. So according to the case 1, if f is continuous on closed AB and k lies between f of A and f of B, we have C lies between A and B such that f of C is equal to k. So f of C is equal to, in place of k we have negative sign minus k. What is this capital F of C? It is minus small f of C is equal to k, and f of C is equal to k in both the cases. So we have f, since f is continuous on closed AB, see here, since f is continuous on closed AB and k lies between f of A and f of B, then there exists C belongs to open A comma B, that is A less than C less than B, such that f of C is equal to k. So this is the statement of the intermediate value theorem. Hope you all guys understand. If you don't understand, watch this video for one more time. So this is the proof from the whole textbook. So thank you so much. If you really like, you know what to do, please make a note of each and every point here. If you don't understand, please watch this video for one more time and pass it on to your friends if you really like. Thank you so much.